All right, I'm going to talk about recommender systems, and in particular, collaborative filtering. It's not something that I dealt with at my work, but I just find it fascinating. It's a way of building ML without having any features, and you will see how. Let's look at this table. This is all you got. You have a table of movies and users. So in this mock table, you have 5 movies, each movie being one row, and 7 users, each user being one column. The values inside are the ratings that the user made for the movie. The ratings are from 0.5 to 5, and the 0 values represent no rating. It could have been null. I think it would make more sense, but here is 0. So what it means here is that user 1 doesn't have any reviews on any of these movies. User 2 has reviewed these 2 movies. Now, you want to build a model that can predict for each of these users what would be their rating of a particular movie. So for a user and a movie, be able to predict. And then you could, the utility of this is that once you have that model, you can run it on all the 0 values to find which one has high expected rating, and then recommend that movie to that user. Now, think about it. If you had some features for the movie, you created some sort of feature set, like the year, the length, the genre, then for each of these users, you could build a model, a linear regression model, and predict. And similarly, if for users you had features, then for each movie you could build a linear regression model and predict what the user would rate the movie with. But in this scenario, we don't have either. And so here are 2 ways we could solve this problem, and I'm going to show you the code for both. The first is to represent movies, and let me backtrack a little bit. The first is to find similarities between movies, between users, or between movies and users. And based on those similarities, I'll be able to come up with some predictions of rating. An example is, if I enjoyed a romantic comedy from 90s, chances are I would enjoy another movie that matches the same description. In other words, if the movies are similar, I will have similar rating of that. So we could leverage this similarity option. That is the first approach that I'm going to continue talking about. Then the question is, how can you find similarity between movies or users, or between movies and users, given that you don't have any features? And that's where the beauty of this collaborative filtering algorithms come in. What we're going to do is represent each movie and each user with a vector. You can initialize it randomly however you want. And then see with the similarity of these vectors that are initially random, what the movie ratings would be, how close it is to the actual values, have an estimate of error or loss, and then take a step in the gradient descent and make adjustments to those vectors, such that by the end of your training process, by the end of that loop, you will have vectors that are actually representative of what the movie rating would be if you find a similarity between those vectors, right? All right. So again, here are the 3 steps. It represents movies and users as vectors. Start with random vectors. Make a prediction about movie rating using these vectors. It's going to be a measure of similarity. And evaluate accuracy, update the vectors, and repeat the loop. All right. Now with that, let's look at the code. Here it is. Import libraries, I'm importing PyTorch for building the model. Here's the data. Let me take a moment to explain this. This is the same schema we went over. There are 4,777 movies. Each row is a movie, and we have 443 users. So each column is a user. And that's what we're going to work with. So I imported that, and I created a train set and test set like you would for any ML project. But this is quite different. You can't split by users or by movies. You actually need all the users and all the movies in both train and test. What I did was that I created a mask, a train mask, and then the opposite of that would be the test mask that just assigns a 0 to some of the non-zero elements and hide them away for training, and then does the reverse for testing. And that way, you know, some of the data points were never looked at during training, and some were looked at only during testing. That's what I'm doing here. Let me run it. All right. I thought, given that we're building a neural net, it would be useful if the target variables are not from 0.5 to 5, but rather average around 0 with a standard deviation of 1. So that's what I'm doing here. I'm normalizing the data. And it comes through. So the mean, by the way, is 3.5 almost. That's the average of movie ratings. And some interesting stuff. Let's see what I got. After you normalize, standardize your data set, your 0.5 becomes -9, your 5 becomes 4, because now everything is scaled and shifted. All right. So the first model is going to be built with the idea of measuring similarities between movie vectors and users vectors. Those vectors have a dimension of 10. You could play around with it to see what would make sense, what would work best, rather. You have, like I said, 4,000 something movies, you have 400, 500 users. And here's the model. Essentially, W is a matrix of the vectors representing users. So this matrix has num-users number of rows, and the number of columns is going to be 10, because for each user you have 10 features, right? So think of W as a stack of users embeddings or users vectors. The p value here, this is a constant that you give to each of those users. So the dimension is going to be number of users, but then a constant value or a single column. And these are the movie features or the movie vectors, where each row is going to be one movie, and for each row you have 10 values or 10 columns, right? And that forward pass is going to be the multiplication of the user's vectors and the movie vectors, and then shifted by whatever that B is. And then you see there are two ways of going it. One is for the forward pass, if there's a particular user you want to get result for, or the entire user base, but the idea is the same. And what I find really interesting here is this x. So this idea of w times x plus b is like the linear regression, right? It's the basic idea. But here it's not quite so basic. It's actually interesting because these features, the x, is trainable parameters, as opposed to other like supervised learning algorithms where the x is given as input data for training. You can think of it as finding the best feature values as part of the training process. All right, here is the loss function. It essentially calculates the mean squared error, and the error is the difference between the predictions of movie rating and the actual values. And then it adds a regularization term. That's it. And I also have a different function to calculate mean squared error so that it doesn't reflect the regularization term in it. And I also calculate the mean absolute error, which I felt like is more relevant for the end user. All right, shut this. So let me go back, make sure I had to pause the video for a second. All right, so with a model randomly initialized, the mean squared error is 18. Let's go through the training process, which is essentially have a forward pass, get the loss only on the training data, even though you made a prediction on the entire data. Do a backward pass, get the gradients, and then update the parameter values once in a while, measure the performance on the test data set and the train data set. So I'm going to run this. And here is the train loss, and here is the test loss. And going down, let's see how things go. All right, I'm gonna stop here. It looks like actually you will starting to overfit, and I'm gonna visualize it too. So if I do this, yeah. So the train and test loss. And by the way, so here the test loss is 7.28. Is it good or is it bad? Let's look at the baseline. And the baseline here is a model that would predict the mean value, and the mean is 0 because we normalize the data for all the input data. So whatever you give to it, it just predicts the mean, and which is around 3.5. See how accurate that would be. What's the mean squared error of that? That's what I've done here. So the mean squared error of a model that is just zero output, the mean would be 7.46. It would be nice to get the model's MAE as well. So let's do that. So where we have a calc, sounds about right. So from 2.12 to 1.79. That's good or bad, that's what it is. And let's see, look at the visualization of the data. But you can clearly see the model is learning from that matrix we provided. And here are the actual ratings. Again, this is normalized, so it's not from 0.5 to 5 anymore. And these are the predictions and you can see that the model has picked up something. And if I plot the errors in a histogram, again, okay, so the blue is the baseline, which is just using the means, and yellow is the model errors. You can see the model errors are primarily around 0, and it just drops off way below the error rates of the baseline model. So it is working. And so that was the first way of solving this problem without any feature sets. There were two ways of thinking about it. One was that you created vectors for movies and users, and you found similarities between these two, and that similarity was a measure of rating. What is really fascinating here is you are using the same vector space for movies and for users. So the users who have similar vectors to the movie will have a higher rating. I think I actually have a visualization of that. Here it is. So this is what we did. We have just assume we have a two-dimensional, in reality we have a 10-dimensional, but two-dimensional vector. Here's a movie 1, and then you have two users. Obviously user 2 would have a higher rating of movie 1 because it's more similar to movie 1. So here's the idea that movies and users are represented by the same nature of vectors. I think it's just very interesting. That means a vector that represents the movie Terminator also represents a particular type of user. Who would that user be, what that persona would be, is a different story, but I find it quite interesting. All right, now take a step back. If you recall, I told you there are two ways I can approach this problem. We covered the first one. The second one is almost the same as what we talked about with one key difference. And here is I'm going to put them side by side so you can see. This was the first one we went over. The second one, same as above, you represent movies and users as vectors, and you also predict how a user would rate a movie, and then you do the backprop and optimization stuff like you would otherwise. The only difference is in this piece, which is how you make a prediction of rating based on the user's vector and the movie vector. And what we did before was that we just multiplied the user's vectors and movie's vector to get a similarity. But here, the idea is a little more generic. The idea is, well, the vector, the elements of the movie vector and the elements of the user's vector, these are just the features that you can feed into your model. Forget about similarity or anything. Just build a deep learning model, feed all these features to it, train it, and see how it works. And that's what I'm going to show next. So here's my second model. The one thing we need to do is to reformat the data. In the first model, the data looked a little unique. You had the same matrix that you use for training and testing, and you had a mask for train, another mask for test. But because this time we're just going to build a linear model, we need to create these X and Y matrices. And the X would be the vectors for, well, each row in the X and each row in Y would be a combination of movie and user pair. And the X is going to be essentially all the two vectors for that user and the movie, and the Y would be their rating. And that's what I'm doing here. I just show you the summary of it, which is Of the 30, I don't remember how many we have, maybe 39,000 non-zero movie ratings. 26,000 are train, 12,000 are test. And if you notice the dimension here, X train has two columns, one for the user, one for the movie. And the Y columns have only one, the Y data sets have only one column, which is for the label. And here is the, I don't know if I ran this or not. All right. Here's how the model would be constructed like. You have a movie embedding and user embedding layers. And these are really the same as what we talked about before. Embeddings are ways of vectorizing these integers, which is the user ID or the movie ID. And what we did before was that we multiplied these two vectors, the movies embedding and the user embedding. We didn't call it embedding, but that's what we did. But here we're not directly multiplying them. We are allowing the model to learn how to combine these together. So once I have these two in my forward pass, I will combine them by concatenating movie embeddings and the user embeddings. So here you have, for each row of data, for each pair of movie and user, you have 10 elements of the user, of the movie vectors concatenated with the user's vector. And then now you have this feature set, just like any other supervised learning problem. We add a bunch of layers for computation. What I did here was that, well, I have a layer that takes all those 20 features, turn it into 10, and then 10 to 1. I played around with it, but let me see what's the, I guess same thing. I could actually delete this. All right, and for the forward pass, you concatenate, call it combined, and then you pass it through this sequential layer, which has two sequential like bucket that has two layers in it, 10, and the second one has a output of 1 because you're just looking for one number, which is the predicted rating. And let's say you build the model optimizer. This is actually quite repeat of what we saw above. Created the model. Let's run the model. And this is the initial model. All right, model training. Just real quick, I had to go back up and rerun a piece of code. I didn't like the error term where I interrupted the training of the first model. So things may look a little different. But for the second model, I did a very similar approach of going through a bunch of epochs, forward pass, calculate the loss, backward pass, and then optimizer step. And this is actually, let's run it from scratch. This is this. Initialize the model. I'm gonna run it for 400. All right, that's it. And this is the loss on train and test. What is of note, let's look at the mean squared error of 5.48 and compare it to the first model. Where is it? 5.63 versus 5.48. And the mean absolute error, which is more tangible, 1.76 versus 1.82. So there's a noticeable improvement in model performance, and if I plot the errors, you see that the errors are all centered, not all, but much more centered around 0 than the baseline model was. So, concluding remarks. We looked at two types of models to predict movie rating without having any information about what the movie is or who the user is. And in both approaches, we vectorized the users and the movies. In the first approach, we looked at the similarities of these vectors. And in the second approach, we just treated these vectors as features, and we built models to ingest the features and make predictions. I like the second model better because it's a lot more versatile. Say if you had some information about the movie or the user, say the user's age, for example, well, you could consider it a part of your feature set and then add it to your model where I was concatenating all the features I had. So with very little modifications, you can actually ingest all different kinds of features, whereas that was not the case with the first model. In the second model, however, you're introducing new learning or trainable parameters that you didn't have to deal with in the first model. So the second model is more prone to overfitting, if you like. What I do find fascinating about the first model, the similarity thing, was it's really interesting that the movies and the users are vectorized in the same space. And as a matter of fact, the rating is measured by the similarity of the user and the movie. So, say movie Terminator or Borat, well, they have a vector representation, but there must be a user who has a very similar vector. In other words, there is a human persona of the movie Terminator or the movie Borat, and vice versa. For any user, there must be a kind of movie that really matches that user. So that notion is kind of interesting. Yeah, I hope you find it useful.